you today about building modern Amiga hardware in 2025. So who am I? My name is Stefan. I am an engineer at Google during my day job. During my nighttime job, I have worked on projects like Coreboot and OpenBIOS, BIOS engineer by trade. These days I don't do a lot of BIOS, but I try to get a little bit closer to the hardware. And in the past I have reverse engineered, together with my friend Chris Hooper, the Amiga 4091 SCSI controller. And today I'm going to talk to you a little bit about what that project was like and where we're taking it now in the future. So why am I giving this talk to you today? I got back to the Amiga community a couple of years ago, and I found it very interesting to learn from this old technology. It's a little bit like learning from an old car. You can still modify things, you can still, the whole thing works, whereas with modern technology, of course, it has become so complex and so complicated that you can maybe touch like one little piece or another little piece over here, but changing the overall thing and doing something end-to-end is becoming incredibly hard as a single person or a small team, a small group, right? And of course, another important part is the community that we enjoy here in the retro computing space. I've found, especially during the pandemic, I found a lot of friends here and built a lot of cool things together, and it's something that's very fulfilling, and it brings a lot of joy actually to see that you start with an idea and at the end of the day you have something in your hand and it does something, it moves electrons around. Another reason for me to be here today is as a child I had an Amiga, of course, but I could not afford a lot of the really cool stuff that was out there. And so nowadays, coming back with having a real job and having a lot more experience than I had before, like building the things maybe that we all wished we had when we were kids, is also a really cool project. Yeah, just generally like the end-to-end process of building stuff. From an idea from the inception to having something in front of you, it's really awesome. So this was me in 2020. I just got to be a fresh Amiga owner again, and there's this story where I tried to get a small expansion for this Amiga, and I asked a friend from Europe to ship one to me because he made them, a couple of them, and he would refuse to send this little hardware to me because he said the hardware is worth less than the shipping that it takes to send it to you, so I'm not going to ship it to you. And out of spite, I bought the soldering iron and I made a couple of PCBs and I started learning how to use this, and I learned hardware is hard. And I definitely, my hands show, I have the scars to prove it. So I coming out of like basically two left hands and not a whole lot of experience, I took online classes from this guy Eckel, who's a pillar of the Amiga community. And he would every Saturday give classes on how to hold the soldering iron, how to solder, what to look out for, how to not destroy your board that you're working on. Start practicing with PCs, then move on to Ataris. In the end, you can have an Amiga. Yeah. And then a little bit later, this happened, right? Like I bought an Amiga 4091 SCSI controller off eBay, and I had met my good friend Chris Hooper, and we were talking and we were looking at this board and we were saying, hey, like all the components on this board are still available, either new or new old stock. We could totally reproduce this. And after a little bit of back and forth and Ami West, coming in between with a lot of people encouraging us to do this project, we actually did it. And as you can see here, this is our reproduction. And the idea for reproductions like this, at least for me, like there's a lot of folks out there in the community that build a piece of hardware. Maybe they design a PCB, right? And then they share the PCB with the community. That's awesome. What we went out to do is, however, we really wanted not to reproduce the piece of hardware, PCB. We wanted to reproduce an experience. There's something that feels like what people would have had back in the 80s, in the 90s, when they got this box in front of them and opened it. And we wanted to get as close to that original experience as we could. And so around 2022, Chris and I, you can see here, are sitting in my garage. Chris brought his table, and we started mass producing a small number of these devices. We got a lot of parts and some pretty nice equipment. You see Chris at his microscope over there. We experimented with solder stencils and hot air, and then went back to manual soldering stuff. So we had a lot of learnings and experiences in this little garage. And so what is it that we were building? And so back on the Amiga, SCSI was still the de facto state-of-the-art storage solution, and there were like on the Amiga there were two types of bus systems that were very common. The first one was Zorro 2, which was used on the Amiga 2000, and then the Amiga 3000 and 4000, the more advanced models, they used a bus system called Zorro 3, and Zorro 3 was significantly faster. So a real 32-bit bus, and it had advanced DMA, and so this is a much more interesting target to build whatever was a high-speed SCSI controller at the time. So we built a SCSI controller that's fast SCSI, so high speed in this case means 10 megabytes per second. You need a fairly decked out Amiga machine, like either an Amiga 3000 or 4000 with the latest custom chips in it. So let me talk a little bit about what it takes to build a product. Right? If you're starting out and you have an idea, like maybe there's something you're missing, or maybe there's something where you're thinking, it's like, hey, this would have been cool if that existed. Maybe don't start designing your dream Amiga mainboard as your first project, right? Choose something that's achievable, that you can do. It can be out there, because we are all standing on the shoulders of giants here, and there are many of us out there, and we like to help each other, and we like to make sure that everything progresses. And so if you find something that's important for you, that like you can connect with, that can help you tell your story or tell a story that you want to tell, that is, I think, the perfect idea for a project like this. And when you're starting out, one thing I want to throw in there is like choose what's important for you, and say if you want to design something that is fast, don't put it on a Zorro 2 expansion card, put it maybe directly on the CPU bus. So collect some information, learn a little bit about how the system overall works, and then refine your idea before you start digging down and drawing up hardware. So as much as there are other steps involved in building a whole product, designing a PCB is a very fundamental piece of this, and especially for the things we are doing in the retro computer space. Now, when you're designing a PCB, there are basically two steps. There are first you draw up the schematics, which are the building blocks where you place logic diagrams, how are components interconnected with each other, and then you move on to routing, drawing the PCB. and actually giving it a shape and giving it like a form factor that then later will plug into a machine, for example, right? And one recommendation I have there for you is like try to finish your schematics before you start routing. I have made the mistake a lot of times that I drew something up and I started routing, and then I had to go back and throw everything away and then start from scratch. And I hear from my famous PCB designers that is something that they face all the time, but try to do yourself a favor and then try to finish one step and then go on to the next step. So the two programs, two pieces of software that I've used to draw up PCBs in the past is KiCad and EasyEDA. There's a lot of others, Eagle, and there's Altium and more professional systems. Often they cost a lot of money. KiCad and EasyEDA are the two that I'm listing out here, because KiCad is entirely open source, and so you have a lot of runway. Like you know that like in 10 or 20 years from now, you will still be able to open your PCB files and still work on them, still understand them. EasyEDA is living entirely in the cloud, which is also very cool. So when Chris and I worked on the first version of the SCSI controller, we worked together, we collaborated on EasyEDA, and think of it like the Google Docs of EDA software. So I could work at the same time as Chris was working on one subsystem, I could work on another, and so we could speed up and really collaborate and bring this to life together, which was also a really great experience. And then as you are building something, one thing I recommend you to think about also early on is, do you want to open source or your creation and share it with the world and share the building plans and the interiors, or do you want to like keep it a closed system? For me, the answer there is very easy. I want my stuff to be open source because I hope that somebody can learn from it and somebody can actually maybe improve it and understand what is going on, maybe fix devices if they break. And then also something, looking a little bit backwards, the original development crew of the Amiga made all of the schematics available to any of the devices. You can find them out there. This is something that is really fantastic, and this is really also one of the key parts that keeps this community alive today. And I think a lot of other computer systems that we use today, like your Mac of the day or whatever, you will not find schematics for your latest MacBook on the internet, or cannot order it in a printed form. And so if something breaks, it's broken. You're never going to fix it unless you are a certified repair shop and you have access to that information, right? And make sure that you put your intention out there early on. That helps obviously also get others to join. When you're getting closer and you want to build your hardware and you know what you're going to build, choosing hardware components is a really tricky part, and that I have personally gone back and forth, especially with the current project where I have tried to modernize the old designs that we were originally replicating. So you will have to look out for speed grades, for example. Many of these chips, logic chips, today's versions might be a lot faster than the chips that we had in the 80s and 90s. And while that sounds amazing, and it's like, why can't we just build a faster thing? In the end, like having everything be faster might also get in your way, so you have to keep thinking about that. Of course, there's stuff like space requirements. If you want to build a PCB of this size, then everything has to fit somehow. The smaller you go, the harder it becomes to hand assemble. The larger you go, maybe it's more tedious while you're assembling. Think about heat production. A lot of the older chips do become really hot, so that was one thing that we learned during our first reproduction project. There are a lot of GALs, gate array logic chips on the device, and they heat up a lot, right? And so a lot of these old machines, they're now 40 years old. You don't want them to overheat. You don't want them to die of a heat death. So trying to lower the temperature in the case is always a good thing to think about. And of course, with heat production, power consumption is also a factor. The less power you consume, the less heat will be produced for the same thing. Nowadays, we also have different types of chips that back in the day, everything was maybe TTL or CMOS logic with 5 volts. And nowadays, there are 3.3 volt chips, 1.8 volt chips, or even lower, right? 1.2, 0.9. Be careful. Like if you connect these new chips to your old logic, you will blow up these chips, right? So you need level shifters potentially. You have to plan that into your design that at any given time you will have the right voltages at the right chips. These overall, these parts, like they really inform the design of your of the thing that you're building. So one thing today that makes building new Amiga hardware a little bit tricky is 5 volt logic is almost dead. It starts getting really hard to get logic chips and CPLDs that are 5 volt either tolerant or operate at 5 volts. So one very popular chip, CPLD, it's a programmable logic chip, which these are fantastic for building new Amiga hardware. They still exist, but they are obsolete officially, and so once the current supply runs out, probably it will be really hard to build new things with them. For now, the next couple of years, I think they're fine. I had looked at the ATF 1500 series chips. These are they can also operate with 5 volts, but for my project now, there were no chips available with enough inputs and outputs to actually solve the problem that I wanted, and I didn't want to put several of them on the board, so they were not a good choice. As far as programming these chips goes, back in the 80s and 90s, WinCOPL was a very common programming language to write logic for these chips. Nowadays, of course, everything is done in VHDL if you're from Europe, or Verilog if you're from the US. It's probably worth investigating if you can use one of the two, if you have advanced logic that you want to use. I think Verilog is overall a little bit easier to write. It's also a little bit easier to shoot yourself in the foot, but that's a good starting point. So another step, the next step up, so you will have to design firmware or software for your card that you're producing. Right? And software development has really changed in the last 40 years, I would say. Like I think when the Amiga operating system was first developed, things like version control was still fairly new, and there were not great solutions out there like Git. Nowadays we have more of I would say an iterative life cycle, right? So every device you build, there's almost an expectation that you will provide firmware updates after the fact once and keep improving the thing. That was a lot harder back in the day, but it's something that really makes this a lot more interesting and a lot more accessible to hobbyists, because you don't have to get it perfect the day you ship your first device. You can keep improving over time. And the people using your hardware will be able to then also easily get a hold of these updates. There's stuff like continuous integration. So one of the things that I am doing these days is whenever I check a change into the firmware, a repository, all the firmwares for all the different devices that I'm building gets compiled automatically and is immediately available on the web page for people to test. I have used static analysis to find bugs in my drivers. There's Coverity, for example, has it's a commercial product, but it has an open source branch that lets you feed it open source software, and it will do the same statical analysis. So you'll find buffer overflows, for example, in your device, or other types of null pointer, potential null pointer accesses and stuff like that. There's, as far as programming goes, there's not a whole lot of Rust or modern programming languages in this space, of course. So there's still a fair amount of assembler, but a lot of the stuff today is written in C, and maybe a little bit of a mix of both. And another super useful tool that I have found is emulators. So whenever I do driver work, I try to test my drivers in an emulator first before I put it on hardware, because it is still easier. Your cycle of testing, changing, testing will be significantly faster. Right? And yeah, make sure to make good use of the open source communities. There's a lot of amazing code out there. There's a lot of amazing people out there that have done stuff that you can learn from, or help you, people that can help you improve and implement the features that you want to implement. Now, say you are done implementing your PCB and you're done writing your drivers. Maybe there's some other work that goes into this project. So in our case, the original SCSI controller that we were duplicating, reverse engineering, had specific metal brackets that were non-custom. You cannot buy them today, so we had to figure out how can we reproduce those. We started out 3D printing them, and that worked, but they were super flimsy, and you plug them in like 2 or 3 times, and they break. And sometimes you can buy off-the-shelf brackets for things. That's something that I've been trying with the new design now, to just lower the costs. If that all is not an option, find a friend that knows how to operate metal equipment. I cannot say this often enough. Find a friend that can help you. Is an important lesson for all of these projects. There are also services out there that let you like cut metal, like Oshcut. JLC PCB can create aluminum PCBs that then you'll have to bend yourself, but they're like pieces of aluminum. You can print stuff on them. So that's also a nice solution for maybe for simpler stuff. If you have a lot of bends, that gets a little bit hard because aluminum is not easy to bend, right? And one thing I found, like a lot of stuff in retrocomputer, especially the plastic parts, when they're 40 years old, they break. You can design new ones. I personally like to print them in nylon or resin because the quality of the parts that come out is really nice. And often it's easier to spray paint them in the right color that matches the tone that you want to reach, rather than trying to find the right filament color. And then still have, you see the filament lines and all of that jazz. So this is how we developed our brackets. Here you see the original bracket in the bottom, and it has these 2 custom cutouts. And in the middle you see my Prusa 3D printer trying to reproduce the bracket. And then we went on and I found a friend, and he made nice laser cut and professionally bent brackets. One of the stories here is that you can see in the top left corner there, these brackets, they have a double bend right where like the connectors sit, so that the connectors don't short out. My friend asked me several times, like, can you get rid of this double bend? Like, this is something that we really don't like. It's hard to do. You need special machinery. So you'll have to think a little bit about how you can optimize the thing that you're doing. In the end, for this project, however, we went for the highest level of authenticity with the original project. And so I could convince my friend to actually take the extra effort and hand bend like these brackets. Yeah, once you come to manufacturing, you're going to be faced with another set of questions, right? Like, do you want to assemble, do you want to get PCBs created only and hand assemble them at home? Or do you want to get PCBs fully assembled? The first cards that we did, we actually went and just ordered PCBs and then hand assembled them. And it turns out there's like 250 components on each of those cards. And it took us approximately, it's a double-sided card, it took us approximately 4 hours per side, so it takes about 8 hours to assemble one card. And then you'll start debugging. And that time goes on top of that. So we did around 30 boards originally, 35 boards originally, and then that became old pretty quickly, right? If you plan on making more than just a few, think about whether you can get the stuff assembled, say at JLC PCB or PCBWay. They're very cheap, very convenient. I tried to get PCBs manufactured in the US. A lot of US PCB manufacturers, actually, they ask you all sorts of extra questions, like how many holes are in your PCB? And I was like, I uploaded my Gerber files. Can't you count yourself, right? So there's definitely, between the different options that you find out there, there's convenience differences, qualitative differences, of course. However, if you want to build prototypes and you want to make stuff cheap, then JLC PCB or PCBWay are really good options. If you make very small stuff, Oshpark in the United States is fantastic. They're fairly quick. Their quality is amazing. Like, they build everything with ENIC, which is gold-plated PCBs, versus the older Hassel stuff that's not gold-plated and harder to solder later on. However, they charge per square inch, and so if you build something that's a little bit of a bigger square, it becomes pretty expensive pretty quickly. And yeah, as I said, like, creating PCBs only is great for prototypes, but you build more, it will get very stressful and very, very tedious. And if you assemble stuff yourself, consider the time you spend on debugging them later on, finding solder bridges and looking at stuff maybe under a microscope, right? And obviously we don't get paid for our time in this hobby, but the time that we are able to spend on the hobby is still limited, and so it might well be worth it to pay the extra fees for getting stuff assembled. Another cost factor here is double-sided versus single-sided assembly. Double-sided, like if you have components on the top of a PCB and on the bottom of a PCB, the cost will go up quite significantly. So if you can fit everything on the top, that's a great optimization. Typically, if you get stuff assembled, also through-hole components, as opposed to the ones that are SMD that you would just solder on the surface of a PCB, through-hole is more expensive because it requires extra processes. And then JLC PCB, for example, has this concept of basic parts and extended parts. And basic parts are the ones that when they make the PCBs, they always have them in their feeders for the pick-and-place machines. So they are very quick to load the basic parts, but extended parts they have to manually load, and so that is also a cost factor. They will charge you for this, of course. Here's a little example of how it is hard to debug after you have assembled for 8 hours. So you can see there's a lot of, in this row on the right here, there are a lot of ferrite beads, but not all of them are ferrite beads, right? That's very easy to overlook because one of them is supposed to be a capacitor. And if you don't have a capacitor there, you're shorting your power rail to ground, and that has very negative side effects for your PCB. So don't do it. So always, before you plug something in, go over all the parts, look at what you're building, make sure that everything looks good before you apply power. Maybe measure your power rails with like with a tool, and then make sure that you can safely plug it in first. Yeah, one thing where we, like, once we had our product done, we were thinking, it's like, how do we get this product to the people? And that's where the experience that we wanted to reach comes in, right? And it's like, how do we package stuff? And first, I was like, well, it'd be nice if we could have the manual that came with the original device and pack it with a card. It took us a lot of time to find the original manual and to reproduce it. And then I was starting to print a couple of copies on my laser printer at home. And I found out that that is not that cheap, actually, right? If you print like a booklet of like 30, 40 pages on your printer at home, that costs a significant amount of money, and then you have to figure out how do you like make a real booklet out of it. There's a lot of manual work involved again. There are services that are actually not that expensive. I found out that for the Amiga 4091 project, or a production project, it was cheaper to get the manuals printed, and then you have like nice options like glossy covers or soft touch lamination, so it feels like a real product, right? And in the end, the cost for getting it manufactured was about a third lower than it would have been if we would have decided to just print it at home. Of course, that, as always, there's an economy of scale here. So if you're only making one manual, just print it. If you're making 30, 40, 50, look at these services. Also, I found a different vendor that would print boxes very cheap than printing the manuals. So compare prices there. The next thing, everything's done. Fantastic, right? Now you gotta ship it. I have to say, shipping companies are ruthless, and they earn money on everything that we ship across the planet, of course. Very often it's a significant percentage of the thing that we're shipping around, right? Like, it seems so easy these days that you buy something online, maybe from China, and it comes to you and it costs like $1 or $5. If you're shipping stuff yourself and you're shipping 20 devices, your shipping cost looks significantly different. So one thing that I learned there is, like, if you want to ship to a large international community, find local partners. Find maybe somebody in Europe, if you want to sell your product in Europe, that can make the stuff there and ship it from there. Or ship like a whole box full of stuff and then have them like send it to the people that want it. That way you can also save a lot of money and make it more interesting. Stay local if you can, and for as long as you can. So if you say you hand assemble, right, buy your parts local, buy your parts from Mauser or DigiKey. If you're assembling in a factory, try to, and the factory happens to be in China, try to like ship all your parts from China, from the warehouse directly to the factory, consign the parts. You will save a lot of back and forth, because every time you leave the country you might pay some tariffs, and like that cranks up pretty quickly as well. And yeah, last but not least here, like, think about how big your thing that you're building really has to be. If you can make it smaller, you will save money on every board that you're shipping out. So this is one of the things that we learned there. We started out with the Amiga 49 reproduction, which was a card like this size. Shipping these things, because it's, I think, like just slightly more than 12 inches long, you're paying basically oversize almost for every package that you're shipping to Europe. That's a lot of money that you're spending there. make it smaller, stay within the limits of what shipping companies can easily ship, and you will be a lot better off here. Yeah, here's my plug for open source. In my opinion, like doing this stuff as open source is really a must, right? Like, and only reiterate, like, all of us that are building this stuff, we're not getting rich of this. And so if you're not making money, maybe you can recuperate some of the costs that you put into building these things, but making this stuff open source, it will enable so many people to come and help you and solve problems that you would otherwise be facing by yourself. For example, one of the things that we came out with when we did the Amiga 4091 board is that a couple of months afterwards, somebody in the German Amiga community came up and sent a couple of patches for the PAL equations, the GAL equations of the logic chips, and said like, hey, here, I made these changes. Now your SCSI controller is about 1 megabyte per second faster than it was before, right? Like, that is something that I would have never come up with at the time, but it was something that now, like, everybody gets the benefits from this. I think these contributions that you can foster there are very valuable. Also, people learn from this stuff. Like, I had many people come and say like, hey, like, now I understand a lot better how a Zorro card works, because now I can look at the schematics that you drew up and the documentation that you have online. Right? And then these same people, they will build another device, and they will build something that you will appreciate. So it's really, you start out and you're standing on the shoulders of giants, but maybe you're a giant for somebody else in the future with the things that you're building. And that can be a lot more satisfactory than just making a couple of bucks more on what you're building. Yeah, I also want to throw this in here quickly, a word about the law. I'm not a lawyer, so take this with a grain of salt, obviously, but the trademarks like Commodore and Amiga are still debated and fought over and shifted around, right? Like, for our reproduction, we actually put the Commodore logo on the box that we reproduced, but like, if you're building something from scratch, like, probably stay away from that. If you feel like you have to do that, reach out to the stakeholders, reach out to the owners. A lot of times, for example, when I built the first Amiga 4091s, the ROM was copyrighted. We didn't have an open source ROM at the time. I reached out to Cloanto, who I believed is the copyright holder at the time. And I got permission to put the original ROMs on these cards. Right? Later we decided that we want to also improve the driver, and so we rewrote one from scratch. Yeah, don't steal stuff. And also, like, if you take something that's open source, don't close the projects. It's not good for the community, and it does not gain you as much as you might think, right? Like, I've seen people building Amiga boards that are based off schematics that you find on the internet that were published by Commodore, published by the Amiga team. And now they're building closed source derivatives of this stuff, and you cannot debug them, you cannot fix them. It's not the Amiga spirit. Now, what we did with reverse engineering, our first thing, because I didn't really know how to create hardware from scratch. So one way of learning for me was by reverse engineering this SCSI controller that already existed. And when you're reverse engineering stuff, you'll have to think about whether you're going to do a destructive or a non-destructive reverse engineering, right? And on the left side here, you see one project by John Hertel. He would like grind down the different layers of the PCB and then take photos of the PCB and then reverse engineer layer by layer by layer. For other stuff, that's not really necessary. So in our case, I was really afraid that we would destroy the one card that we had, and then once we would get far enough along to actually debug, we wouldn't have a reference that we could compare it to. So we were very careful. We took some parts down, we desoldered some of the parts so we could see the traces under these parts. But then the board was still a 4-layer board. And so what you see here on the right is I used a very strong flashlight to figure out where the traces on the middle layers were. And that was luckily enough in our case, that was good enough to actually fully reproduce the board. When you're reverse engineering, when you're building hardware in general, there's a couple of tools that come in very handy. If you get your hands on one, get an oscilloscope, get a logic analyzer. There are some very cheap logic analyzers. I put a link in here. I looked online, like you can get an oscilloscope for as low as $40, right? Maybe logic analyzers are a little bit more expensive, but you get solutions for under $100 for either of those two. And they're not as good as the professional ones, but they will get you a long way. This is when we first had our board working. The board would show up on the first boot. And then I tried to start talking to it, and then it would suddenly stop talking to me, right? And so here's my attempt to hook up my logic analyzer and figure out which ones of the gals was not functioning the way it was supposed to. Make sure also when you're designing stuff from scratch, put test points on your board so that you can get to the signals that might be interesting to you. I want to throw this in here. Like when you're professionally building PCBs, any electronics product, there are different cycles that the industry follows, where specific tasks are assigned to each of these cycles. You don't have to follow this. For example, like when we built the Amiga 4091, we built prototype boards and then we fixed a bunch of things and we went pretty much exactly to mass production, right? But there are a couple of steps inside, like prototypes are typically for prototyping. You build something, you see if it works, is it possible? Then like you come to this, the engineering verification test, EVT. You'll try to validate your design, make sure that everything is sound. By DVT, you should have basically everything working. And PVT is then more of a like pre-production run of like, hey, like this is getting serious. You'll build a couple the same way you would build the final product. Try to think of like risks that are applied. Like if you see instability with your design, like don't start mass production, right? Like go back to the drawing board, see if you need to do more validation, see if you need to like change the design itself. Is the takeaway here. And this is important. Do reviews. Get stuff reviewed. Get a second set of eyes, find a friend, find somebody that looks at the stuff that you draw up, because you will miss stuff. And if you have more friends, show your schematics to each of them and say, like, hey, can you look over this? We found a lot of different, in this latest project, we found a lot of stuff that was hooked up incorrectly. And then we were able to fix it. However, in the end, like 2 things were still wired up incorrectly, and so then you have to deal with reworks later, then you have to do another run of PCBs. So find people that help you look at this, because you will become blind at looking at the same stuff over and over again, and you will not find the critical mistakes you might have made. And read the data sheets. This is a mistake that I have made. I read the first abstract of the data sheet, and it's like, oh, this part is 5-volt compatible, and it can also work with 3.3 volts. And then I put the part down, and I operated at 5 volts, and it didn't see any of the signals. Because the signals coming in, yes, it takes 5 volts and 3.3 volts, but if you power the part with 5, it won't see your 3.3 volt signals reliably. That was another rework we had to do. Yeah, and ask people around you, right? There's a lot of good knowledge out there in the community. Yeah, design for manufacturing. At some point when you want to build this stuff, the first couple you build will be super fun. If you build dozens, hundreds maybe, it gets old pretty quickly, and so reducing the effort it takes to make a PCB, that also needs to be part of your development cycle there. Because you'll get, eventually you'll get boards back, right? You assemble a board, it's not working, what's the problem? You find the problem, you move on. You'll get returns, like somebody puts this thing in their computer and it doesn't work, they'll send it back to you and say like, hey, it's not working. How easy is it for you to repair these things? And so that's definitely like, try to come up with a design that's easy to assemble, easy to manufacture, and that can mean something different for depending on what you're building or what your own skill set is, right? Your own skill level. Maybe you don't feel comfortable soldering SMD parts, you're comfortable soldering through-hole parts. Then you will probably end up mostly assembling the stuff in your garage or whatever. But sometimes soldering SMD parts is a lot easier and quicker. So, and then like if you put stuff only on one side, again, like your cost will go down significantly. So keep these things in mind as well. Yeah, I mentioned this a little bit already. Here's a pretty good comparison that I saw the other day of like the different parts that you can find. There's TTL and CMOS parts. There's like the low voltage TTL parts and some lower voltage parts that you can also find. If in question, look at what qualifies as a clear 1 or a clear 0, or what qualifies as somewhere in between, right? And then read data sheets, make sure that what you're building, that you're always, that the different parts that you're using are always playing nice together. And then when you're looking at how to manufacture stuff, you'll have to purchase parts at some point. Now, if you get assembly at JLC PCB, most likely they will have a lot of the parts already that you can just order through them. Their hardware vendor, parts vendor is LCSC. If you need more rare chips, like our SCSI controller chips, we bought them from UT Source and then had them shipped directly to the factory and consign them at the factory. So that's something you can do where you say like, hey, I need 20 parts or 100 parts. You ship them to the factory. They will do an intake. They will make sure the parts are okay, and then they will solder them onto your design. The very rare stuff you'll find often on AliExpress, and if you're going with modern parts that are still available, DigiKey and Mauser for purchasing locally are very good choices here. And here's another thing that I learned with the latest design. I started out and I was like, well, I need a couple of transceivers and I need I don't know, so and so many inputs, right? And I needed 3 large parts, and then I was like, oh, but this other large part is like half empty. I'm going to put a smaller part in there. Then I did the calculation later on, and I found that buying 3 parts of one type and 1 part of another type, if you're building only 10 of these, you're going to end up being more expensive than you put 4 of the larger parts on there, and then you get like a rebate for buying more parts of the same type. So also look out for that. Yeah, you can consign parts for assembly, and yeah, definitely avoid double taxation and tariffs on this stuff. If you ship stuff from the United States to China, ship it back, ship something else to China, ship it back, like it becomes very, very expensive. All right. The next generation. This is the latest SCSI controller that we have built. As you can see here, it's very similar to the Amiga 4091 that we previously had. One of the key changes is that we moved all the GALs into a single CPLD Xilinx that you see here on the left side. And we got rid of a bunch of other parts that are not needed in the new design. There were little jumpers on the side that we also moved into software handled by the CPLD. A flash part, so you can update the software on the fly. And so just trying to get to like a more compact, more modern design overall. And here's a picture from the bring up, or like this purple PCB that you see on top is a device that emulates a SCSI hard drive, and it's small enough to just conveniently sit on top of the PCB there. Yeah, there were like a couple of challenges that we faced during the bring up of this board. So when I was still drawing up schematics, and I thought I was done, and then all of a sudden, like shortly before we wanted to tape out, I found that I was missing 8 data lines that connected the autoconfig data to the bus, because we moved the autoconfig data from the ROM into the CPLD. But the CPLD didn't have any of the data lines that were actually required to feed that information back to the Amiga. Whoops. That was a big one, and of course that was one of those things where it requires then to reroute the whole board, basically, right? And another thing is like Verilog. It's fantastic. It looks like software. You write stuff, and it feels like almost like writing C or assembler. And it's like, hey, if this is that, then set this other thing. That can burn you, and it. In my case, it literally almost did. Because you can configure your CPLD in a way that you connect ground to your power rail, and then your chips start burning up. So it looks like software, it's not. Be careful. And one thing I also learned is there's a couple of configuration registers in my Verilog code now. These configuration registers, they take up a lot of space. So when I started out the project, and I tried to make an estimate of, hey, what chip do I need? And I thought, like, my chip is probably not going to be more than 30% full. We just barely got it to fit in the end. And configuration registers, where you write a value from the Amiga or read something back, that takes a lot of space, right? And yeah, these, as I mentioned earlier, low-power chips, they're not always no-brainers. They might betray you and not see your signals correctly in weird ways. So here was my first round of debugging, was debugging by thermal camera. So I plugged the device in, put my first version of Verilog on there, and then I saw that the temperature, here in the picture you can not really see it anymore, but the temperature went up within seconds to like 80, 90, 100 degrees. So I took a picture, turned the device off, changed my Verilog code, flashed it again, put it on there, and then the picture happily looked different, but now a different chip heats up. Right? So that was like my first couple of iterations, like, hey, I need to get this thing stable, and now I can start actually trying to look at how is it communicating. Yeah, and here's a picture of a rework where the top signal was connected to the wrong line. You can see it's cut out, like the trace is cut up there, right under C401. And then we had to connect the trace from the next pin that also had the same signal. These are not too hard, but like this is something that you don't want to sell things like this, right? Or have your community have to add these reworks. So try to prevent these. Here's another one. This was my mixed low voltage chip that I thought can do 3.3 and 5 volts. It works better if you connect it to the 3.3 volt rail, as you can see here next to the LDO. Yeah, sorry, I'm hurrying up. Okay. Yeah, we did just here the new features that we built for this latest card. Actually, like now we have flash memory on the board, so we can update, and the dip switches are also software controlled now. We still have our boot menu. And there's a couple of side things that came out of, side projects that came out of this project now. So one of the things is I ported the driver that we had to the Amiga 4000T. So you can now also flash a new kickstart on your Amiga 4000T and, for example, boot from CD-ROM. Or you can also do other projects. We have like one project where we're replacing the SCSI controller chip with a NCR 7070, which is an ultra-wide SCSI controller. So these things now, because there's a large basis of code already, like these things are fairly easy to support actually. Yeah, just quick, so ultra-wide SCSI is on the table for the next board. Just max out the speed that we can reach on these devices, right? And make it more resilient, make it work on more Amiga machines. Bus timings are always a little bit critical, especially on the Amiga 3000. And just also continue to reduce the cost of the whole thing. And at this point, I want to say thank you to the crew that has been working on this. Yeah, so Chris, who's also here today, and so I think everybody except for Dorkin is here. So thank you guys all for coming. Sali has been making hundreds of these boards for us. The whole project could not have happened without him, right? And of course, Chris was a major pillar. Without him, like, I would have never even started this project. I want to say a special thanks to Monse, who is a professional PCB designer, and she designed, after I was done drawing up the schematics, she routed the schematics. She was always patient with me, messing up my signals and rerouting the board like 3 days in a row every single day. And the board looks amazing, so I can't wait to share it with you all. And then Dorkin, a guy from Germany, sorry Dorkin, I don't have your picture, but he helped a lot rewriting the original logic in Verilog and taught me a lot of things along the way there too. Yeah. And there's also a lot of other people that have contributed in one way or another to this project, so thank you all for making this a community effort and a really cool project. Yeah, please join us. Come online, join the ACL Discord, or hit me up after the talk if you want to know more about the project. And yeah, you don't have to know everything, right? Like, that's exactly the point. Like, it's about learning, it's about building new stuff. And that's it. Thank you.